This is Algebra 2 at Trig, section 7.7. We're going to write and apply the exponential and power functions. For this first question, we're looking at the points 1, 10 and 4, 80. Essentially, we're moving over 1 and up 10, over 4 and up 80. We have these 2 points. Whenever you have 2 points, you could draw a line between 2 points. You could probably make a parabola through at least those 2 points. But what we're going to try to do is make an exponential equation. So we've drawn the graph in. Now we need to know the equation that would best fit going through those 2 points but still be exponential. So what we're going to do is use this format, which is y equals ab to the x power. That's what makes it exponential, because your variable, your x, is in the exponent. The 2 points we have given to us are x and y and x and y. So we're going to come over and say that y equals ab to the x. When we plug in the y value, we get 10. We don't know the a or b, and our x value is going to be 1. And we can write another equation. We can write the y value is 80, a times b, the x value is 4. So now we've plugged in our x and the y, but we still don't know what the a or the b value is, so we can't write the equation. So we're going to bring this equation and solve it for a. So we're going to take the 10, divide it by the b to the first power. Divide that underneath. That leaves us with just a. We'll bring down our second equation and bring across this one. So we have 80. The a value is going to be plugged in as 10 divided by b times b to the fourth. We can rearrange that to say 10 times b to the fourth over b. So now that's going to become 80 equals 10b cubed. We'll divide both sides by 10 and get 8 equals b cubed. And we can take the cubed root of both sides to get rid of the cube around the b, because we want to get the b all by itself. So that leaves us with 2 equals b. Now we know what the b value is. So to figure out the a value, we'll bring down this equation, and we're going to bring through what the b value is. It's 2. So I know that this should be 5. So a equals 5 and b equals 2. So to write our equation is y equals a, which is 5, times b, which is 2, to the x power. Now remember, order of operations says that we cannot multiply 5 times 2. That is not 10 to the x power. Let's try to set up this next one. We know that we have x and y, and another x and y. So using my format of y equals ab to the exponent of x, we'll plug in 8. And we'll divide by b. So now we have a. We also have our other equation, which is 32 equals ab to the second power. Now we're going to bring over this a, which is 8 divided by b, times this b squared. And when we simplify, we're going to end up with 8 times b. And in this case, we can divide by our 8, and b equals 4. There was no need to do a radical. I know that 8 divided by 4, because it's 8 divided by b is 4, that's going to equal 2. So my final equation is a is 2 times b is 4 to the x power. You can always test it by taking your points in and seeing if it works. Plug in a 1. 4 to the first power is 1. 4 to the first power is 4. 4 times 2 is 8. Plug in a 2. 4 squared is 16 times 2 is 32. So you can always verify if these equations are accurate. On the next page, we're going to be looking at an equation, or actually the graph. Here we see a bunch of points. We're given a table down here. We have a bunch of points, and we're trying to decide if those points are going to make a good exponential model. They're just a group of points, and maybe a line is the best fit for that, or maybe a quadratic is the best fit for that. If it is truly exponential, then when you take the natural log of the y values, that should realign those points and make it a straight line. So we can test that using our calculator. We're going to have L1 and L2. And then we'll plug our x's and our y's into our calculator. So with our calculator, we're going to hit the Stat button. That takes us into this menu. We hit Edit. We need to type in the 0, 1, 2, 3, 4, 5, and 6 for the 6 different numbers. Then we type in our y values. After we get all our numbers in, then we'll go back up to the Stat button. Move over to the Calc. We've done several of these. We've done linear regression, quadratic regression, cubic. We're going to go down to number 0, which is exponential regression, because we're working on an exponential equation. If you put your information in lists 1 and 2, then you should be set. Some calculators will have multiple rows. It'll start out with L1 and L2, and then eventually down here it says calc, or calculate. So you get your equation. So we have 17.56 is our A value, and 0.913 is our B value. So we're going to bring those and put them as our equation. That is the exponential equation that would best get close to those points. Now let's see if those points are a good example of that. One way to represent this is we're going to do the natural log of all of our y values. And then if we graph those, if it's linear, then that's a good representation. That data was a good representation of something that's exponential. So we'll bring back our calculator. We'll go to Stat, Edit. Now notice in L2 we've put all of our y values. So we can go over to L3. If you go on top with the L3, on bottom you'll be able to write an equation. So I want to do the natural log. So I hit natural log while I'm up on top of the L3. And we want to take the natural log of all of the y values, which are all the L2s. If you look on your calculator, there's a blue L2 above the number 2. So you're going to hit the second key and number 2, and that'll put an L2 on your screen. If we hit enter, it will calculate the natural log of each value that was in L2. So we'll put those down onto our table. So we put those all on the table. Now if we try to graph those, at 0 we could be up at 2.8. At 1 would be at 2.7, 2.6, 2.59, 2.50, 2.4, 2.3, and you can tell by looking at those points that that is very much a linear representation of the points. It's not curving. Each of the values in the y seem to be dropping by pretty close to 0.1 or 0.8, so it's pretty consistent. So that would show that the original data is a good representation of an exponential. So because the graph of x comma natural log of y represents a linear line, then the original data is confirmed to be exponential. It's a good exponential model. Now we're going to look at example 4. We're going to do a power function. The power function is y equals ax to the power of b. Notice the difference, the order that we have. Before, the b was down with an exponent of x. Now we have the x down with the exponent of b. So this is called a power function. We still have our x and y, and we're trying to see what would be the best power function that would be represented by going through those 2 points. So just like we did before, this time we have y ax to the b. We're going to plug our y values in for the y. We don't know our a. The x value is 4 to the power of b. We also have another point, 15, a, 8 to the power of b. So we're going to bring this down, which turns out to be getting the a by itself. 6 divided by 4 to the power of b. Now we're going to take that and plug it in very similarly like we did before. We have 15. 6 divided by 4 to the b times 8 to the b. We're going to reorganize that a bit and say 6 times 8 to the b, 4 to the b. And we can reorganize that since both the numerator and denominator have an exponent of b. I can pull that b out. We're using the property that allows us to distribute it in, the quotient property. Now I can see that 8 divided by 4 is 2. And my goal is to get the b by itself. So I'm going to divide by 6. And I'm left with 2 times b, or 2 raised to the b, equals 15 over 6. You can reduce 15 over 6 if you like. Now, what are we going to do next? Can we divide by 2? Can we take the square root or the b root? No, not so much. We're solving for an exponent. To solve for an exponent, you have to use a logarithm. We've said that throughout all the lessons. A logarithm always equals the exponent. So the base is 2 of 15/6, and that's going to equal the exponent. Well, now I have a logarithm. I have the b by itself. Now I have to figure out what that b actually equals. So log of 15/6 divided by log of 2 is going to equal the b value. So that b value is going to equal 1.322. And that was by using our calculator. So next, we're going to take that b value and plug it back in like we've done before. Bring this guy down, and a equals 6 divided by 4 to the b power. And that's 1.322. Now I would suggest to use the real value there. In the real value, we calculated out the 1.322. So now we're going to say 6 divided by 4 raised to the, and I would put down answer rather than putting in a rounded decimal. And that gets us our answer of 0.96. Notice if we use a number that's a little bit different than that, if we use 1.322, we get a value that's pretty close to it. We'd probably round to that, but it's not that value. That's the advantage of using the answer key. So we know that this becomes 0.96. That's the a value. So y equals a times x raised to our b value, 1.322. We'll try that again. We're doing a power function, x and y. So just to remind myself, a power function has x raised to a power. So I plug in my 8, I plug in my x. Now I'm going to get the a all by itself. So to get the a by itself, the 3 has to go to the bottom. So I have 8 divided by 3 to the power of b. Now I also have 17. My x value is 6 to a power of b. So I'm going to plug this in over here for the value of a, and when I do that, I can reorganize it. So I have my 8 times my 6 to the power of b and my 3 to the power of b. I can pull the b out, and I have 6 divided by 3. So now I'm going to have 2 to the power of b. That is not 16 to the power of b. I have to divide by 8. And then what would I do next? What am I trying to accomplish? I need to figure out what b is. So I'm going to use a logarithm, base 2 of 17 over 8 to equal the b value. To do that, I'm going to use the change of base formula. And we figure out that the b value is going to equal 1.087. So next, what do? We need to figure out what the A is. The A value is 8 divided by 3 to the 1.087. And I would use the real answer there, not just the rounded number. And when we do that, we get 2.42. So our final answer is y equals 2.42 x raised to the 1.087. If you were ever to do a calculation to see if it equals the 3 and the 8 or the 6 and the 17, you need to use the real values of A and B. Okay, this time we're doing our transforming power data. We're trying to see if this data is a good representation of a power model for a power function. So we're going to do the same type of typing our values into our equation. We're going to say stat edit. Let's type in our numbers for x. This time we start with 1 through 6. And our y values so we have all our numbers in. So we can go back to stat, over to calc. Now when we went down to 0, we got exponential model. It's called exponential regression. And now we're going to look for a power regression. We want a power equation for this. So we're using L1 and L2, so I don't have to type anything additional in here. And it gives me our equation and what format our equation is in. So our A value was 7.92. Our B value is negative 0.768. So our equation, I'm using 3 digits here just to be as accurate as you can. 7.92 x to the negative 0.768. That would be our model that we would suggest to represent that. Now, like we did before, to represent a power model, we need to check to see the natural log of x and the natural log of y. So I'm going to come over to stat, go into edit, in list 3, I'll get up on top of L3 and say natural log of second number 1. That put in all the natural logs of my x's. And when I move over on top of L4, I'll say natural log of all my L2s, which are all the x's. I'm sorry, all the y's that time. So we can type in, we see that it's 0 and 0.69 and 1.10, 1.39, 1.61, 1.79. Those are my natural log of my original x's. So now we have 2.07, 1.54, 1.23, 1.00, 0.83, and 0.69. So let's try to graph those. So at 0, we're going to be up at 2.0. 0.6 will be up at 1.5. At a little bit past 1, we'll be up at 1.2. At 1.3, we'll be up at 1. 1.6 will be up at 0.8. And at 1.7, we'll be at 6.9. So if you notice, if you kind of zoom in there, I'm just plotting points on a graph, but those are pretty linear. So that means that the data that they had in the beginning is actually a good representation of a power model. Okay? Because the graph of natural log of x comma natural log of y represents a linear line the original data is confirmed to be a good power model.